Okay, so tutorial 2, we have 3 questions from week 1 and we have the rest of the questions from week 2. So first start with the week 1 question. This is identifying the soil. So we know they're asking us the following sieving analysis and Atterberg limit results were obtained from 3 soils A, B, and C. Hydrometer tests were conducted on the material and passed the number 200, that is uh, 75 micron sieve for soil A and C. So you can see this one. Passing from this one is only for A and C and nothing is passed through soil B. There is no particles passed through the 75 micron sieve. The ratio of the clay to silt is 4:1 for soil A and 1.5:1 for soil C. Classify each of these soils according to the USCS classification system. So that's what we need to do. So here we know the classification system. So here we find out first is the soil sample obviously highly organic with odor, leaves, twigs, etc. So here we are finding out whether the soil is peat or not. So we can see if this is a visual inspection. If they haven't mentioned about this stuff, we assume that it is not a organic soil. So we go in the we go with the no, and we are not going through this for many of your cases. Normally, we don't get organic soils. So now we need to find out how much as sieve test is made on the entire sample and the percentage passing through the 75 micron sieve, we find out that whether it is more than 50% or whether it is less than 50%. If you go to our sample, our readings here, we are now looking at this one. So passing through, they have given us the mass retained, but here we need to find out passing. So we need to find the passing. So we'll first need to calculate the passing. So here, this is what we have. So passing, we need to find this. We can find it in 2 different ways. We can find out the percentage retained or as mass passing. So this is mass retained. That day we did mass passing and we converted it to percentage passing. Now we can do either that way or this way. So we are going to do the percentage retained here. So this to find the percentage retained, I'll do for 1 here, and I think you are okay to do the rest of the things. And you can check your answers. I have the answers and I'll show you. So if you consider soil A, this is the mass retained. So if you add all the numbers here, we can find out how much of soil was there. So if you add all these together, I think you get 199.8 grams. So this is the total amount. Out of this, 0 is retained in this first sieve. So you can see percentage retained will be 0 out of the 199.8 as a percentage. So you can say this is 0%. Retained is 0%. Percentage retained is 0%, nothing retained. And then for the second one, that will be 20.2 over 199 times 100. So that you can find the percentage retained for this one. If you put this in the calculator, that is comes as 10.1%. And the next one is 25.7 over 199.8 times 100%. So that will be, if you do that, it will be 12.9%. So likewise, you calculate all of these ones. And when you calculate the percentage retained for A, B, and C in this way, you will get these numbers. So for A, you get 0%. We already did 0%. And then you get 10.1, 12.9, 20.2. So did you get these numbers, Luke?
Yes, I did. I got exactly the same.
Okay, that's good. So now we need to convert it to the percentage passing, because we can follow that flow chart when we know the percentage passing. So percentage passing here, so 100% is your total. So 100 minus 0, everything passed through from the first sieve, so 100% pass through. Then the next one will be 100 minus 10.1, so that will be 89.9%. And then 89.9% minus whatever the retained percentage, 12.9, and that will become 77%. Now 77 minus 20.2, because 77 is the passing percentage and this one is retaining in the next sieve, so we minus it. So that will be 56.8, and the next one will be 47.7, and this will be 34.1. Did you get the same numbers?
Exact same answer.
Okay, so that's good. So we know the method and these should be your answers. Now we need to look at this particular sieve and percentage passing. If you look at all of these three, A, B, and C, percentage passing is less than 50. So now when we go back to this one, that will be less than 50. So they are coming to this side. So in this chart, this part is for gravelly soils and sandy soils. G and S is in the right hand side, and the left hand side is all these ones, these ones here. So they can be silt, they can be clay, or they can be organic soil. So peat is already gone here up. So our all three soils that we have as samples can be gravelly or sandy. So prefix is GOS. And now let's find which one is what. Then we need to find, so we have sand, gravelly soil, coarse grain soil that can be gravelly or sandy. So now we need to find out from the 4.75 millimeter sieve whether the percentage passing is more than 50. Now let's go back to that percentage passing from the 4.75. So 4.75 percentage passing. Will be percentage passing from the 4.75. That is 100, 100, 100. So they all three will be more than 50%. So that is all going in this way. Am I right?
Yep.
Now we need to find out 4.75 percentage passing. Now we need to find out, so they all are sandy soils. That's why we have so that's why we have all passing more than 50% from the 4.75. So they are not gravelly. They don't have anything more than 4.75. See, 100% is passing from the 4.75. Now, if you look at, so the first letter for all three, A, B, and C, first letter is S because they are sandy soils. Now we need to find out P200. P200 is this one, 0.75, whether the passing is less than 5% or not. So if you go to, again, our we have the calculations here. So here percentage passing for this one is less than 5 for B and C, but more than 5 for A. So here less than 5, yes. So this is B and C come to the left-hand side, and no for A goes to that side. Now we need to, let's start with the A now. So now we need to look at whether this is more than 12 or not. Yes, it is 34.1. So More than 12, yes. So we go this way. And now we need to find out the plasticity index and where it is in the diagram. So this we are looking at this chart, and A line is this line. So we need to check whether the point is above the A line or below the A line. So we in this graph we have liquid limit in the x-axis and the plasticity index here. So liquid limit and the plastic limits are given to us. So if you look at our question, liquid limit is 23%, plastic limit is 8%. So our plasticity index is the liquid limit minus the plastic limit. So we already know that we found it. We discussed that before. So that will be 23 minus 8, which is equals to 17, am I right? 15, isn't it? 23.
16.
23 minus 8, isn't it? 15.
23 minus 8. Oh, yeah, 15. Yeah,
15.
sorry.
So
Yeah.
plasticity in this index is 15, and plastic limit is 8, and liquid limit is 23. So liquid limit is 23 somewhere here, and the plasticity index is 15 here. So that will be above the A line. So it is above the A line, and we'll go to this one is easy. So above the A line, and OPI plasticity index is less than 4. Plasticity index we found it is 15. So none of these conditions are satisfied. So no. So we are going in this way. And then above the A line, yes, above the A line, or plasticity index is more than 7%. Both are satisfied, but we have O here. So yes, so our soil is the second letter for our soil is C. So that will be SC. Are we good?
Yes.
Okay, now in the second one, sorry, B and C, we came to here. Now we need to look at the CU and CC. So we don't have gravels, we have sandy soils. So CU should be 6 for sands, and CC should be between 1 and 3. Oh, so to become well graded. So we need to find out, and actually this is not both should be satisfied to become well graded. Now we are going to check CU and CC. So we already know what is CC and CU. So we need to plot the graph to find it. So I told you we can plot this graph in Excel. Only thing is this is a log scale and this is the normal scale. So y-axis percentage passing is normal scale and x-axis should be log scale. So you need to plot a semi-log graph. We have graph sheets with x-axis log scale, or else you can do it in Excel. Excel, we can change the x-axis to log. So let's do for 1. So we are done with A. So we don't actually need this A graph. We only need the B and C. So this is our B. Let's do with the B. So we need to know D30, D60, and D10. So D10 is where your percentage passing is 10%. And that corresponding size is your D10. And we need to know D30. D30 will be this number here, 0.4. And D60 will be this number, which is 0.71. So using these numbers, we can calculate the CC. So we calculate the CC. We are looking at the B now. CC, that will be D30 will be 0.4. We need to take the square of it. D60 is 0.71, this one, and times 0.18. So CC we can find it as 1.25. And then when we look at the CU, that will be this one, D60, which is 0.71 over 0.18, and that is 3.94. So let's take these two numbers. We'll do the B now. Now, when you go to here, CU should be more than 6. So our CU is less than 6. And also CC should be, both should be satisfied. If one is not satisfied, we go to the no side. So they are poorly graded. So B is a poorly graded one. And if you look at C, I think in the answer sheet, these numbers are different for B, but C should be right. I need to correct it. So if you look at C, CC is, so this is our D10, D30, and D, so this is our curve. Let's say, so this one is okay. And this one should be this. 60 should be this one here. This one, not this. Okay. This one is for the other one is for the A. We don't need A. We already done A. So CC is, now we can have 0.195 squared over 0.4 times 0.42 times 0.42 times 0.71, and CU will be D60, which is 0.42 over 0.18. This is 4.2 and this is 0.91. So if you look at these two also not satisfying both the conditions. If you go to here, it is no again. So the CE also sandy soil, and the prefix is P. So you can see here P is poorly graded and S is sand. So prefix and suffix we got as SP for both B and C, and we got SW for SW. Let me check. No, it's not SW. What did we get? SC. SC stand for C stand for this with plastic fines. So A is SC, B is SP, and C is SP as well. So we have classified the soil according to the unified soil classification system. So are we okay with that? So that covers whole one part.
Yes, I.
Okay, so that's good. Now let's move to the second question. So in the second question, it's a very easy one. It's the Kasaganda test. And they are asking, the Kasaganda test, I hope you remember. We have a bowl, we put our soil here with different moisture content. We blow it and we count, we make a groove first and we blow it. We are counting the number of blows required to close the gap along 12.5 millimeters. So for different moisture contents. So here, when the water content is 52.5, only 6 blows required. When the water content is 4.7, 12 blows required. So likewise, we have for different water contents, how many blows are required, we found it out. But the liquid limit is the number of blows required. So when the number of blows are 25, what is the moisture content? So this we call the liquid limit. So we like keeping the numbers like this, we can't find it. So what we need to do is we plot a graph. So in the x-axis, we need to have the moisture content, and in the y-axis, in the y-axis, we have the moisture content. In the x-axis, we have the number of blows. So we if we don't get a straight line, what we need to do is we convert the x-axis to log scale. But in our case, I think when you plot it, you get um, a straight line. So corresponding, when your x-axis to 25, you can find this moisture content, that will be your liquid limit. So you can find the liquid limit like this. So this is the graph and your liquid limit is 40%. So they are asking you to find the liquid limit, that will be 40%. Then they are asking if the natural water content is 38% and the plastic limit is 23%, calculate the liquidity index. So,
So 40 minus 23.
no, we have a different liquidity index is the moisture content
Oh, sorry. Yeah.
minus you have this equation, okay? You can
Yeah.
find this equation. So
My
this is
bad.
the equation for liquidity index. So you can just substitute the numbers. So moisture content is 38, plasticity index we found 15. Sorry, plastic limit. This is a different question anyway. So plastic limit is 23 and we divide this by 17. So you get a number, I think it is 0.88. And depending on this one, now you need to look at this, this one here. So if your liquidity index is between 0 and 1, your soil is plastic. Plastic or brittle, they are asking, you need to first find this. They are asking whether it is plastic or brittle. Plastic failure, brittle failure. Plastic means when applying force, you can change the shape. Brittle means when applied force, it is breaking. It's like glass. So in our case, this is within the limit. So liquidity index is between 0 and 1. So our soil is plastic. So we can say it doesn't have a brittle failure. Make sense?
Yes.
Okay. So did you do this question? Or do you
Yeah,
want
I
to
did
write
all of
down?
these. I did all of these. The next one's basically the same, isn't it? But
Yes.
you're
Yes.
only finding the liquid limit.
Liquid limit, and the only thing is this is not the Casaganda test, this is the penetrometer test. So cone penetrometer test. So you have to find out, you find out the moisture relevant to 20 millimeter depth of penetration. So here it's lying between these two. So again, you need to plot the graph and you need to find the corresponding moisture content for 20 millimeter depth of the penetration. So that will be your liquid limit. You need to remember this for cone penetrometer test, you have to find for the 20 millimeter depth. And in this one, you need to find for 25 blows. You are going to do this test in the lab. Normally for the same soil, we get same answers, similar, close answers from both the tests because it's the same soil. We'll do this. Okay, so I think when you do that, yeah, you get about 60, 58 or something close to 58 here. Yes, the graph should be
Yeah, I
in
got
the other way
58.
around because when the moisture content is high, the penetration is high. In the previous one, when the moisture content is high, number of blows is less. So here, sorry about it. So your graph is in the other way around because of when the moisture content high, penetration is high. Okay, so that's from the week 1. Now only we are starting the week 2 questions. So here we did a question like this in the on Tuesday as well. Sorry, Monday. So here a dry mineral has a mass of 250 grams, absorbed 150 millimeters of calcium ions with atomic weight of 40. Determine the cation exchange capacity of the mineral. So this is the equation we have. So this is 1000, you already know. And this one is valence electrons 2. And the molecular weight is 40 here. Atomic weight is 40 here. And this is the mass of iron. So 150 milligrams, we need to make it to grams. 150 is needed for 250. So for 100 grams of soil means you need to times by 100 and divide by 250. So this is the amount absorbed for 100 grams of soil, neutralize 100 grams of soil. How many grams needed from the cation solution to neutralize 100 grams of the soil. So that if you put everything together now, you have 2 times 1000. 2 came from here, 1000 came from here, and we have 40. When you put these numbers in the calculator, you get a number that will be your cation exchange capacity. Are we good?
Yes.
Next question, what is the isomorphous substitution in clay minerals? They are theory, okay? Now onwards theory. I hope you remember we discussed about 2 types of clay minerals, tetrahedral and octahedral. So in both we have if a silicon atom is substituted by an impurity, so here with an aluminium or here with an magnesium, then we call that isomorphous substitution. Whenever we have an isomorphous substitution, the negative charge will increase. I hope you remember this part. So they are more reactive. When we have isomorphous substitutions, the soil is more reactive. So what is isomorphous substitution in clay? And you can write an answer. You can show the pictures and you can write it in words as well, a small description. Do you remember this part, Luke?
Yes.
So it is the process that substitutes one atom for another in a structure of clay mineral. This leads to a net negative charge in the mineral. Examples are the substitution of aluminium or silicon ions in the tetrahedral, and magnesium and ferrous and ferric and other aluminium ions in octahedral within clay minerals. So they are the substitutions. Sixth question, explain why some 2-to-1 clay minerals have high shrink swell capacity while 1-to-1 clay minerals do not. I hope you remember the sheets. 1-1 means you have, it's like this, gypsum and silica sheets 1-1-1. And here 2-to-1, silica sheets 2 and gypsite sheets 1. So when we have sheets making layers, so when sheets are together making layers, so you can see here in between this structure in the kaolin, if you can remember, we have strong hydrogen bonds. So water can't easily go in here because it's bonded. So they are the activity is less. But if you consider elite, we have potassium ions here as the bond. So we, in the previous question, we discussed when there is an impurity, the negativity will be higher, more reactive. So water can, compared to the previous one, water can absorb to this one, active with the water. So they are absorbing water and releasing water. So it is swell, it is shrinking and also swelling. When water absorbed, it is swelling. When water evaporated, it is shrinking. So you need to have water to shrink. So here we have less water in the kaolin. So if you have less water, then it is not shrinking or swelling much. But if the amount of water absorbed is higher, then when it is evaporated, shrinking is also higher. And also, if you look at the montamonorite, we call it bentonite. The market name is bentonite. You have very weak van der Waals bonds. between this one. So again, it is very reactive because the surface area is too high compared to the 1:1:1. And so when we discuss, when the surface area is high, specific surface area is high, water can wet the outer surface and it is more reactive. So they are also shrinking and swelling quickly compared to 1:1 clay structures. Are we good?
Yep.
I think I have explained everything, but just reading this, okay? The 2:1 clay that shrink and swell have an interlayers that can be penetrated by water and hydrates iron. Two layers of oxygen atoms face each other across the interlayer space. So that is the structure that we have here. Here, the structures that we have here. Two layers oxygen atoms face each other across the interlayer space. They are slightly negative and repel each other, making it possible for the clay to shrink and swell. The 1:1 clay are built differently in this. The layer of hydroxyl molecules face a layer of oxygen atoms across the interlayer space. The hydrogen atoms from the hydroxyl and the oxygen atom in the opposite sheet forms hydrogen bonds, so resulting in strong interactions and lack of shrinkage and swelling. So that because of the bond in the hydrogen bonds in the kaolin. Okay, so the next three questions are MCQ questions. So indicate which of the following statements are true. The absorbed water imparts plasticity to clay soil. The absorbed water imparts plasticity to clay soil. Is it true? Fine grain soils have large surface area than coarse grain soil. We already discussed that. Kaolinite has less swelling properties. We already discussed that. So isomorphous substitution will increase the negative charge of the clay particles. That's also we discuss. So that's all theory. This part I already discussed in the previous one. So in the second one, indicate which of the following statements are true. Isomorphous substitution will decrease the thickness of the double diffuse layer. Clay are composed of, you can do some research on this one. We didn't discuss about this, some of these ones. Clay are composed of three main types of minerals. We discuss it. The engineering properties of fine grain soil does not depend on the mineralogy factors. Is that true? Clay minerals, we discuss about the gravitational forces and surface forces. Which ones are predominant for which type of soils, gravelly or sandy or clayly soils. So we discussed that part. Clay minerals consist of silica and aluminium gypsum sheets and sheets that are combined form layers. We discuss it. You already know. So you should be able to, these kind of questions are in your quiz as well. Indicate which of the following statements are true. The bond between interlayers in montmorillonite are very strong. So we already discussed it. So we have weak van der Waals, and in kaolite we have hydrogen bonds. Water can easily enter between the interlayers in montmorillonite, causing swelling. We discuss it, why it is happening. We talk about it, and that's a very active weak soil, but we are using that for other applications to make an impermeable layer. Dispersive clay is susceptible for erosion. Is that right? Dispersive soil and fabrics, flocculated ones. Dispersive is very it can disperse in with water. It is erosion can easily happen. Dispersed structure develops when clay have been reworked or remolded. So we discussed that as well. So, yes, so that's all we have. This all theory we discuss. I think you have a better understanding because we have discussed all the theory and also we did most of the numerical questions covering the theory. And the equations that we use in the week one, we will be using next week onwards so that you will get familiar with those equations more in coming weeks. Okay, so
Okay. Thank you for the tutorial.
yeah, I went fast because you said you already tried the questions.
Yeah. Yeah.
But
I'd
if
already
you
done
want
question.
me to explain anything like into a depth, we can discuss as we have time. It's still 6:40.
No, I think I'm good. If I've got any questions, I'll send you an email.
Okay,
Thank you. I'll see you Monday.
see you.
Bye.
Bye.